Hi, everyone. My name is Joe Morton. I am a junior in mechanical engineering at Mines, and this is my presentation for the Mines Undergrad Research Symposium. My project was on additive manufacturing of high-pressure components for nuclear power plants. So let's get started. What is additive manufacturing? Additive manufacturing can be broken down into three main types. There's metal powder bed fusion, metal injection molding, or MIM, and direct energy deposition, DED. Now, pictured to our left is the part that we are researching to try and produce eventually. So what is wire arc DED? So first, we need to discuss really what DED is. For this application, we used automated gas metal arc welding, or GMAW, as you may hear in industry, where weld beads, or the filament or wire that I was talking about earlier, are layered on top of one another. Let's watch this video to our right here, where we can see in real time, well, slow motion, not real time, where the arc is melting the filler metal and going into a weld bead, and we can see the molten pool of metal where the arc and the filler metal are drawn to this pool, and the weld bead is made, as it is called. So why would we use DED? DED is much more cost effective for two reasons. One, it takes less time to make product, so more products per same amount of time. Now, for this project, the goal is to try and make replacement components, not mass-produced components, but the amount of time to make a DED manufactured part, then trying to go make a one-off cast part, as many of these pressure components are made, is a tenth the time. And then the cost of equipment compared to other metal additive manufacturing equipment is much less, as you can see when you have a wire and an arc, it's a little less complicated than having a powder bed. And for our application, the wire and arc, as it's shown in the video to the right, is all in one. An automated GMAW, or in our application, we were using a MIG welder, has the arc coming straight from the filler rod, which is acting as the electrode, which is that more perpendicular looking piece in the video. And the electrode will produce the arc that will melt the filler rod, but if they're all in the same piece, it's like having a 3D printer nozzle, and it can follow its track and just layer by layer. So beginning my research, my team needed a way to create beads to look for oxidation, splatter, and various thermal properties that we could study further to look at later on when we would begin building walls and hopefully eventually making parts. So how am I going to do this? So we need to control travel speed, all the welding parameters, and hopefully basic automation, so it would be as easy as the push of a button. So to do this, the welding center had a Fanuc ArcMate 100i. Now this is a robot that has been adapted by Fanuc to use a welding power supply that will be automated just like a MIG welder or a DED machine. And it can travel in 6 axes. So when I started, the machine had been dormant for a very long time, and the power supply needed to be changed so it would be synchronous to Oak Ridge and our other experiments. And the user interface was kind of hard to learn at first, as there wasn't very good documentation, and compared to some of my other experiences using CNC milling machines, not a lot was in common. So then we started to have the debate on whether it was easier to use the ArcMate and try to give it an operated tool path or try to make my own gantry. It was very quickly determined that me making my own automated gantry system would be more work than necessary for our application. As for the ArcMate or the machine I may create, there was no practical way to give it an automated tool path using any common or modern software. So as we can see in the picture to the right, this was the initial test rig for making basic weld beads to look at the splatter, thermal and various properties that would be important for my team to look at going forward. So after working on the robot, it was very clear that using this simple gantry would be perfectly fine for making a single weld bead. The speed was set with a potentiometer knob and an on-off switch and direction travel. So the height was set with a simple clamp, and you had to hold the trigger just as if you were welding normally. So this is a great way to get some initial beads. Now, the first round of testing, we used the initial parameters as provided by Oak Ridge that they had been using. So this was using a shielding gas of 95% argon, 5% CO2. The wire was 316L stainless steel. The surface travel speed or weld speed was 40 inches per minute. And that was set with that potentiometer knob on the gantry. The feed rate for the wire was 400 inches per minute. And the welder mode, this is a Lincoln setting, was 284. The Ultimark setting, which I'll explain later, was 0. The trim was 0.9, which I'll also explain later. And then the more classic welding parameters, or a power supply, was at 200 amps and 28 volts. So relatively high to some sheet metal, but well within reason for how thick this material would be in a nuclear power plant. So what is Ultimark? And Ultimark is a manipulation of the welding arc or waveform of what will be given to the electrode from the power supply. So as we can see to the right, this is an image of how the Ultimark setting can change from the lowest to the highest. And at 0, there's also a small kick at the end of the trailing edge of the peak of the wave. So the initial parameters had it set at 0. So it had the kind of medium slope, but then it had that extra kick at the end before it would reignite. So a little more of like a pulse width modulation with a lower peak in the second half. Then at -10, we had a shallower slope on the leading edge and a longer lead off time on the trailing edge. And the opposite was true for the +10 or high setting. Now, the trim setting, as discussed before, actually has to do with the frequency. So how many times are we going to see this peak? So looking ahead at what those had effect on, the low trim or high trim had a significant impact. And that can be as expected, as if you compare a low frequency weld to high frequency weld, the high frequency has a tendency to be more consistent and clean. And as we can see, it has much less splatter and seemingly much better heat control. And that can be shown, the splatter can be seen by those dots on the left side or the lack thereof on the right side. And the heat control is the more similar coloring on the images to the right as opposed to the left, where it seems like we have a cold region in the very middle with seemingly hot on the bottom and edges. And on the right, on the high trim or high frequency, it's much more consistent. Now, the Ultimark setting had a little less impact, but you can actually see a more significant change from samples 1 to 2 on the left, where the +10 Ultimark setting had more desirable thermal properties from that bead. And as you can see below, runs 3 and 4 had a larger bead width, which is consistent to higher heat at 0.747 meters and 0.72, and 1 and 2 were shallower. And runs 3 and 4 had higher current and voltage values. So what are the next steps? Now that we've generated some good base bead settings, now it's time to start building walls. And building walls is how DED really works as you start to build parts. And so the image to the left is the first wall that we have made, and then this will be converted into test specimens to be used in mechanical testing. And also, obviously, smaller samples will be used for electron microscopy or X-ray diffraction, as the initial X-ray diffraction testing was very difficult trying to analyze the weld bead on this base plate. So what can we do as further experimentation or research past these weld parameters? Um, the shielding gas has stayed the same this entire time. So the 95.5 gas has not been changed, and there's been nothing to try and reduce outside contaminants. So one idea is to make a housing to create an argon bath where you try and immerse the entire piece in argon. So there's very little chance of oxidation. Um, and then the next step would be to look at more complex heating or cooling control to preserve the optimal temperature of these layers. So before they cold set or they're too hot, going from layer to layer, so you have more inconsistent bead layering. And that can be very important if you're trying to hold a more specific tolerance, which would be true of this pressure component. And even if that's not necessary and there's currently a machining operation that's designed to do that, maybe this would reduce machining time. And then the next has to do with strength testing, and varying the weave pattern to improve strength could have a lot of possible benefits. So if you look to the picture at the right, this seems to be some kind of nozzle or pressure component, and it doesn't seem like that width of the top coupling or back coupling is the size of a filler wire. So if you have to weave back and forth, using different types of weave would be great to test on what is the best for strength or speed, whatever your safety factor allows for. So that was it for my research. I hope you enjoyed this and that it was informative, and thank you for watching.